In this video, we're going to take a look at applications of universal gravitation, and a topic that most people find interesting is the International Space Station and being in orbit. So one of the first questions that comes to mind is, what keeps the satellite up there? ISS, International Space Station. So yeah, okay, we can address that question, but also I'd like to phrase it in another question, is that why doesn't gravity make it fall? Right, so let's try and do just one-word answers. What keeps the ISS up there? Nothing. There isn't any force keeping it up there. Well, then why doesn't gravity make it fall? And the short answer to that is it's busy. It's busy providing the centripetal force. So now if we can go ahead and take a look at the universal law of gravitation and its role in an orbit, we can, as always, start off with Newton's second law, which says F net equals ma. And then gravity's down, and the centripetal acceleration is down in this case. So we can write minus the force of gravity, excuse me, is equal to mv squared over r. And it's a minus sign because it's also downward. Now we could write in mg here, mass of the satellite times gravity, 9.8. But we have to remember that 9.8 is only valid at the surface of the Earth. It's not valid when we're, at some altitude. So instead we can turn to the universal law of gravitation, and of course the minus signs cancel out. And so this is going to be big G M E little m over r squared, and then that's equal to m v squared over r. So this is the universal gravitational constant. This is the mass of the Earth. And this is the mass of our satellite, and this is the radius of the orbit, like that. Now, it's important to separate out these two ideas. So there's the radius of the Earth, and then there's this little piece that we usually call altitude, or h, or height. And it's the combination of these two that form the radius. Okay, so having described that a little bit, let's carry forward. Well, we see some cancellation, so the mass of the satellite cancels out. So nothing about the orbit is dependent on the mass of whatever's in orbit. Could be a tiny microsatellite, could be, could be something as massive as the International Space Station, which is at this point over 100 meters long. We have one factor of r that cancels as well. And if we're trying to solve for v, we can now take the square root of the whole thing. And that means that v is equal to the square root of g, mass of the Earth, and then radius of the orbit. So this is the speed that's required for a stable orbit. So let's check out and see what the altitude of the International Space Station is. So I'm just going to share my screen really quick, and we'll go and take a look at a tracker that tells us where the International Space Station is. Okay, so I took this link and I pasted it into Canvas. So if you want to, anytime you want to check this out, you're welcome to. And so this is can be qualified as a low Earth orbit. So currently the latitude's around 41 degrees north, and it's over Japan right now, and then it's nighttime. Nope, sorry, that's where it's going to be in an hour and a half. The yellow line is where it is right now, and it's about to cross the terminus, which is going from the shadow of the Earth into sunlight. And the altitude is listed right here at 423 kilometers. The speed, of course, we can check that out later. So it's incredibly fast, 27,000 kilometers per hour. But if you were going to go around the Earth once every hour and a half, you'd be going that fast too. Okay, so we'll utilize that 423 kilometers. Okay, I'm going to stop sharing our screen right now. We can go back and take a look at that. Great, so I've got 423 listed here. That's in kilometers. And so we're going to multiply that by 1,000. Okay, so there we go. And then we know the mass of the Earth is up here. By the way, I incorporated a PDF that's got a handy dandy reference for the masses and other planetary data. And that's located in Canvas as well. It looks like this. So if you want to use that, you're welcome to. So it's just a real simple tabulation of some useful planetary data and information about the sun. Great, so let's find out what the speed of the International Space Station is supposed to be in SI units. So for starters, we have to figure out what R is. We have the radius of the Earth, and then the altitude is 423 kilometers. So we'll take the radius of the Earth, that's 6.378 times 10 to the 6. And then this unit of study where you have to deal with a lot of large numbers. So I'm going to just do a quick reminder about how to do scientific notation, because we're going to add these two numbers together. So the proper way to do scientific notation on this calculator is to go 6.378 E6. Okay, and then so that's going to be 6.801 times 10 to the 6th power. Okay, good. And we know the mass of the Earth. So now, in order to calculate the speed, we're going to fold that in. So 6.67 times 10 to the minus 11. And the mass of the Earth is 5.972 times 10 to the 24th. And then divide by the radius, which we just got, so 6.801 times 10 to the 6th power, and then we'll take the square root of the whole thing. And we'll see that, what that equals. So first of all, just again, a reminder, 6.67, and then we want to use we want to try and type this in. So in Texas Instruments calculators, we're going to use the double E key to get that. And in Casio's and other products, there's probably a key that says EXP or something like that. I'm just going to store this as a letter in the calculator, so I don't have to keep typing that in all the time. And now I can just use G. And I'll do what's underneath the radical first before I take the square root. So times 5.972 EE24 divided by 6.801 EE6. Okay, so that's what's underneath the radical. So now I'll take the square root. Okay, so 7 653, and that's in meters per second. So let's convert to kilometers per hour, and we'll see how close we got. So if this is in meters per second, and I want kilometers per hour, so I'm going to divide by 1,000 to get to kilometers, and then I'm going to multiply by the number of seconds in an hour. Yeah, so 27551 kilometers per hour. And then if we want to do miles per hour, then we're just going to divide by the number of kilometers in a mile, which is 1.609. So 17,123 miles per hour. Yeah, that's pretty fast. Let's just go back and see how we did. We can query the International Space Station and see where it is now in a couple of, oh, so now it's just south of Alaska and it's making its way towards the West Coast. All our satellites, for the most part, except for the ones that are circumpolar, travel from west to east. And this is because when you're launching it, we can make use of the fact that the Earth is rotating towards the east to get a little boost. And there's actually a lot of stuff up there, so it's a subject for a conversation later, but let's just see. So 27588, let's go see what we get, 27551, so pretty close. All right. Let's continue this example one more time, and let's find its period, t. So speed equals distance divided by time. And this is a special distance, the circumference, so 2 pi r. That's assuming it is actually a circle. It is actually, in practice, an ellipse. And we use capital T because it's a special time. So if we're solving for t, then that's 2 pi r over the velocity. And so 2 pi, radius 6.801 times 10 to the 6th power divided by the sizzling velocity of 7,653 meters per second. Right, okay, so there's my 7653 right there. So 2 times pi times 6.801 E6 divided by 7653. And that's in seconds because we are using SI units. I'm going to round that off to 5,584 seconds. So that looks pretty good. Let's convert it to minutes and see what that looks like. So we'll divide that by 60 seconds in a minute. Yeah, so 93 minutes. Or 1.55 hours. Okay, so that's a good example of using the universal law of gravitation and taking a look at what the cause of orbit is and some of the properties.